Imagine meeting someone at a party. You start chatting, and within minutes you realize they're not from around here. Not from your city. Not from your country. They speak differently. They dress differently. Their entire vibe says foreign. That's 3-Iatlas. When scientists analyzed the gases coming off this comet, basically taking a chemical fingerprint, they found something that screamed alien. Not alien as in little green men. Alien as in this thing was not born in our solar system. Every comet we've ever studied is mostly made of water ice. Frozen H2O, the stuff you put in your drinks. But 3-Atlas? It's spewing carbon dioxide, CO2, the gas you exhale, the stuff in soda. 8 times more CO2 than water. That ratio doesn't exist here. It's the chemical signature of a place so cold, so far from any star, that water barely even exists. A place where carbon rules. Iatlas didn't form around our sun. It formed somewhere else, circling a different star, billions of years ago, and somehow it traveled across the void between stars and arrived here. In 2025, right when we have the technology to see it. So here's the question. Is that timing a coincidence? Or was it always heading here? Before we dive into the chemistry that reveals where 3-Iatlas really came from, I'd love your help. If you're finding this story as fascinating as I am, hit that like button. It genuinely helps more people discover these questions. Drop a comment with your take. Random cosmic wanderer or something more intentional. And if you want to keep following this investigation as it unfolds, subscribe and turn on notifications. Your support keeps this channel going. Thank you. Now, let's talk about what makes 3-Iatlas chemically impossible for our solar system. What comets are made of, the basics. Think of comets as dirty snowballs. That's not an insult, it's actually a pretty accurate description. The standard recipe. When our solar system formed about 4.6 billion years ago, there was a giant cloud of gas and dust spinning around the young sun. As things cooled down, materials froze. Close to the sun, it was too hot for ice. That's where rocky planets like Earth formed. But farther out, past Mars, out in the cold zones, water froze. And there was a lot of water. Hydrogen and oxygen are 2 of the most common elements in the universe, so H2O ice was everywhere. Comets formed in these cold regions. They're basically chunks of water ice, the main ingredient, dust, tiny rock particles, frozen gases, like carbon monoxide, ammonia, a bit of CO2. When a comet gets close to the sun, the ice heats up and turns into gas. That's what creates the glowing coma, the fuzzy cloud around the comet, and the tail. Why water? Dominates in our solar system. Water ice is king. It freezes at 0 degrees Celsius, 32 degrees. Out in the cold zones beyond Mars, temperatures easily drop low enough for water to freeze solid. Carbon dioxide freezes too, but at much lower temperatures, around minus 78 requesters, minus 190 degrees Celsius. There's some CO2 in comets, but it's always the minor ingredient. Water is the star. Scientists have studied hundreds of comets, and the pattern is consistent. Typical comet, maybe 80–90% water ice with small amounts of other stuff mixed in. CO2 to water ratio, usually around 110 or 120. Water dominates by a lot. This isn't just true for a few comets. It's true for all of them. Every single one from our solar system follows this recipe. Until 3-Atlas. The chemistry that doesn't fit in. August 2025, the James Webb Space Telescope pointed its instruments at 3-Atlas. Webb doesn't just take pictures. It breaks down light into a spectrum, like a rainbow, but way more detailed. Each chemical element and molecule absorbs light at specific wavelengths. By looking at which wavelengths are missing or present, scientists can figure out exactly what a comet is made of. It's like reading a barcode that says, "I'm made of this, this, and this." What Webb found, the data came back. And it was shocking. Carbon dioxide, absolutely dominant. The strongest signal by far. Water, barely there, faint, almost an afterthought. The ratio, about 8 to 1. 8 parts CO2 for every 1 part water, that's backward. That's not how our comets work. Why this matters. Imagine you're a doctor. A patient comes in and you run a blood test. Normal human blood has certain ratios. Iron, calcium, proteins, all in expected ranges. But this patient's blood comes back completely wrong. 8 times more of something that should be rare. Almost none of something that should be common. You'd immediately think, this person isn't from around here. Or something very unusual happened to them. That's 3-itless. Its chemistry is wrong for our solar system. Where does CO₂-rich chemistry come from? So if 3I-Atlas didn't form in our solar system, where did it form? To answer that, we need to understand what kind of environment creates CO₂-rich ice. Temperature. Is everything water freezes at 0 degree C, carbon dioxide freezes at minus 78.8 degrees C. That's a huge difference. In our solar system's comet-forming zones, temperatures were cold enough for water to freeze easily. CO2 froze too, but water was so abundant that it dominated. But imagine a different environment, a place where temperatures are even colder, way below minus 78 degrees. Water is scarce or locked up in other forms. Carbon is more abundant than usual. In those conditions, CO2 ice would form first and in greater quantities. Water would be the rare ingredient. Possible birthplaces, option 1. Interstellar space. The void between stars is incredibly cold. Temperatures hover just a few degrees above absolute zero, minus 270 degrees. In that deep freeze, all kinds of molecules freeze solid. Water, CO2, carbon monoxide, methane. If 3I-Atlas formed in interstellar space, maybe in a cloud of gas and dust drifting between stars, it would have formed under these extreme conditions. Carbon-rich chemistry would dominate. Option 2. Around a dim star, not all stars are like our Sun. Red dwarfs, for example, are much cooler and dimmer. A planet or comet forming far from a red dwarf would receive very little heat. In the outer regions of such a system, CO2-rich ices could dominate simply because temperatures never get warm enough to favor water. Option 3. A dying star's outer disk. When stars age and expand into red giants, their outer layers cool. Material in the far reaches of these systems experiences bizarre chemistry. Carbon gets enriched, oxygen gets locked into compounds, and the usual water-rich recipes break down. A comet forming in this environment could end up with the backward chemistry we see in 3I-Atlas. The bottom line, wherever 3I-Atlas formed, it wasn't here. It wasn't in the warm, water-rich environment that shaped our comets. It came from somewhere cold, somewhere dark, somewhere far away. The interstellar journey. Let's say 3I-Atlas formed around another star, or in the space between stars. How did it get here? Getting kicked out comets don't just decide to leave home. Something has to give them a push. In a solar system, the most common culprit is gravity. A large planet, like Jupiter in our system, can gravitationally slingshot a comet, flinging it out into interstellar space at high speed. This happens in our solar system all the time. Jupiter acts like a cosmic bouncer, tossing out comets that get too close. Some of those comets end up on paths that take them out of the solar system entirely. If 3I-Atlas formed around another star, a similar event likely happened. A giant planet, or maybe a close encounter with another star, gave it a gravitational kick. And off it went, into the void. The long journey space between stars is vast, unimaginably vast. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. That's 40 trillion kilometers, at 68 kilometers per second, 3I atlases, current speed, it would take about 18,000 years to travel one light year. If 3I atlas came from even the nearest star system, it's been traveling for at least 75,000 years. More likely, it's been drifting for millions of years. During that time, it traveled through the cold, dark void. No sunlight, no heat, just endless emptiness and background radiation. And then, in 2025, it arrived here. The timing. Question. Here's what keeps astronomers up at night. The universe is 13.8 billion years old. Our solar system is 4.6 billion years old. Humanity has had telescopes for about 400 years. Advanced space telescopes like Webb have existed for less than 3 years. Atlas could have passed through our solar system at any point in those billions of years, but it didn't. It arrived now, right when we can detect it, right when we can analyze its chemistry, right when we're looking up and asking, are we alone? Is that coincidence? Maybe, or maybe 3I atlas knew when to arrive. The chemical fingerprint. What else is hiding? The CO₂ dominance is the headline, but there's more in the data. Subtler signals, things that don't quite fit even the interstellar origin story. Rare elements. When astronomers analyzed the spectral data in detail, they found trace signatures that shouldn't be there. Organic molecules, complex carbon chains. Not just simple CO₂, but longer structures that form under very specific conditions. In our solar system, these molecules are rare and usually indicate ancient chemistry, material that hasn't been altered much since the solar system formed. In 3I atlas, these organics appear in concentrations higher than expected, as if the comet carried pristine material from its birthplace. Unchanged, unaltered. Isotopic ratios. Different atoms of the same element can have different numbers of neutrons. These are called isotopes. For example, most carbon is carbon-12, 6 protons, 6 neutrons. But some carbon is carbon-13, 6 protons, 7 neutrons. The ratio of carbon-12 to carbon-13 varies depending on where and how the material formed. Atlas isotopic ratios don't match solar system norms. They're off, shifted toward values seen in interstellar clouds or in material around other types of stars. What this means. Chemistry is like a birth certificate. It tells you where something came from. Atlas chemistry says, not here, and the details, those rare organics, those shifted isotopes, add layers to the story. This isn't just a chunk of ice that got kicked out of another solar system. This is material that formed under conditions we don't see in our neighborhood. It's a sample of alien chemistry. Literally. Why does this matter to us? You might be wondering, okay, it's from another star system. Cool. But so what? Why does this matter? Understanding our origins water is essential for life. At least, life as we know it, if comets delivered water to early Earth, and many scientists think they did, then understanding where comets come from and what they're made of helps us understand our own origins, but 3I atlasis different. It's water-poor and carbon-rich. If a comet like this had bombarded early Earth instead of water-rich comets, life might never have formed, or it might have formed differently. Carbon-based, yes, but using different chemistry. Different building blocks. Studying 3I atlas gives us a glimpse of what other solar systems are like, and by extension, what other planets might be like. The search for life. If we ever detect life on another planet, we'll need to understand its chemistry, what it's made of, what it breathes, what it eats. 3I atlas is a chemical sample from another star system. It's a tiny piece of an alien world. By studying it, we're learning what normal looks like out there, and that knowledge will help us recognize life when we see it. The arrival. Question, and then there's the big question, the one that feels almost too big to ask out loud. If 3I atlas came from another star system, traveling for millions of years, and arrived here just as we're capable of studying it. Is that luck? Or is something else going on? Conclusion. The Stranger from Another Star, August 2025. The James Webb Space Telescope analyzed the chemistry of 3 Iatlas, and it found a fingerprint that doesn't match anything in our solar system. 8 times more carbon dioxide than water. Isotopic ratios that scream interstellar origin. Organic molecules that shouldn't be there in those concentrations. Iatlas wasn't born here. It formed somewhere else, around another star, or in the cold void between stars. In an environment so different from ours that its chemistry is backward. It traveled for millions of years, across distances so vast that our minds can barely comprehend them, through the empty, silent darkness between stars. And it arrived here. Now, in 2025, right when we're looking. Is that timing a coincidence? Maybe. The universe is big, and coincidences happen. Or maybe 3 Iatlas is more than a wandering snowball. Maybe it's a messenger, carrying information written in chemistry, a sample of another world, a piece of a star system we've never seen, and maybe, just maybe, it was always heading here. Subscribe to Narrator of Shadows, because when a stranger from another star shows up at our doorstep, we need to ask, what brought you here? The chemistry says, I'm not from here. The timing says, but I'm here now. And the question that remains, why?